my name is Ricardo, and I'm your host of Math Matters. And today I'm here to talk to you guys about RSA encryption, and specifically a worked out example of numbers I chose to demonstrate how RSA encryption is carried out. So, the first three numbers that I had to choose were Bob and his numbers. So those are P1, the first prime, P2, the second prime, which I just chose as 11 and 5. 11 and 5 are two small prime numbers, but the only important part about that is the product them. P1 times P2, which is 5 times 11, or 55. So that means the mod we're taking it to is 55. Now, this is important because the modulo we're taking it to means, based on our modular math example up there, and based on the first video I made describing modular math and how it can be used in encryption, this means that when we take the mod 55, we're dividing by 55 and then saying what the remainder is. So the answer of our mod problem is what the remainder is. Once we have the remainder and we have the mod, to a spy who is again looking at all our transactions in cyberspace, or looking at all the communications that occur in cyberspace over the internet, to a spy who gets, let's say, the mod and even the remainder, they have no way of telling what the number itself is, because for any remainder and for any mod, there are several different multiples that can get you the same remainder. So for instance, in this example, 41 mod 4 is 1, because 41 divided by 4 has a remainder of 1. 41 mod 4, and that means that 4 goes into to 41 10 times to make 40. So it means what's left over after you divide 4 as many times as you can, and that's 1. Here our mod is 55. However, there is the third prime number that we have to choose, and normally computers automatically generate prime numbers, which are very easy to do, and they can multiply prime numbers, which is also very easy to do. Most calculators can do that already. So computers, with a lot more processing power, can also do that. Generating a public key is also very easy, and it's the third prime number. So the third prime number I chose was 3, and that's our public key B. So, again, our public key is used to lock the message or encrypt it, whereas our private key, which is the last number, unlocks our message once Alice sends it back to Bob. So, what is this private key? What does that mean? Well, like I said, it's based on the P1 and the P2. That's why we have to choose two different prime numbers. Why don't we just choose 55 right off the bat? Well, P1 and P2, like I said, Euler's function, there is a formula, or not even a formula, there's a step-by-step solution to get this private key, and at the end I'll show you how amazing this private key can be in unlocking this function very easily. But to the spy who saw this transaction, saw this communication happen, where Bob gave not only his mod, but his public key, with which Alice is going to secure, encrypt, protect the message. These two things were given to Alice so she can protect the message. Now the spy has B, the public key, which is 3, and P1 times P2, which is 55. However, it's very important that they don't know P1 or P2. In this case, if you see 55, you would probably know that the two numbers are 11 and 5. However, with a giant number, and I'm going to mention later on, I'm going to explain how big these numbers can get, just how big they can get, how difficult it is to factor such a prime number. For instance, it's rather easy. We can do it in our heads, computers can do this in milliseconds, but for numbers of the caliber with which computers deal with every day, factoring this number here is impossible. And that's important because if you know P1 and P2, you can get the private key, thus rendering this whole complicated process useless. Because if the private key is really powerful for Bob, it's also really powerful for the spy. So this wants to say private, hence the name. So Alice now has B, the 3, and P1 times P2, 55. So in this equation, she has the mod with which she's taking it to, and she has the power. Now her message is 4. I just gave a simple number because most data can be expressed in terms of numbers. Usually it's zeros and ones, which is in binary, and that correlates to a number, which again correlates to whatever data they're sending. So let's say the message is 4, that's what they want to send, and we manipulate it using math. So not only here are we using modular math, but we're overcomplicating it, or we're making it even more complicated, which is kind of the point, right? We want a computer who has no access to the m, we want a computer to make it as difficult as possible for that computer to solve for the m, just by brute force, which is what we call trying every option. We want to make it as difficult as possible to solve for this. So raising it to a power achieves that end and makes it really, really hard. So let's rewrite this. We know our m, we know our b, we know our mod. Therefore, m is 4 to the power of b, which is 3, 4 cubed, mod 55. It's a bit sloppy, but this is where our calculators come in. So, this short example is a very good example of how we can do mods on our calculators. Most calculators don't have a mod button, unfortunately, but it's very simple to do if you know what mod means. So it literally means this number divided by the mod, and then what's the remainder? Well, that number, 4 cubed, is 64. So this is 64 mod 55, what's the remainder? Well, if you think about it, there's only, when you divide 64 by 55, it only fits in once. That's kind of intuitive, but we can divide it out and see what happens. 64 divided by 55 is about 1.163, etc., etc. So it fits one and then a little bit. So we want to know what that little bit is. Now, because if it's 1, we can just subtract 64 by 55, find what the remainder is that way. Or, what works for every method ever, for any number and any modulo, and for any message, what works all the time is subtracting the whole number, which is 1. So you have 1.16364 decimal. Subtract the whole number, making just the decimal, so 0.163636. Multiplying that by your mod, and that gets you the remainder of 9. So that equals 9, which is otherwise known as our C. So obviously the remainder of 64 after you divide by 55 is 9, because 64 minus 55 is 9. It's a good way to check yourself here. But now 9 is our C. Well, let's think about what our C is again. Our C essentially is this locked box. There's a box in which m is held, and you can't see it, and then it's locked using the public key. So it's in a box, and it's locked, and then it's sent over to Bob. So we're going to try erasing this. It's a bit tough to erase, but we now know our C is 9. So she sends this to Bob. And Bob, who's been asking for the C from Alice, now knows the C is 9. Notice, the only person who knows what the message is Alice. The message is nowhere in cyberspace, and it's important to note that the spy, who is constantly monitoring cyberspace, has no idea what the message is. He only has these 3 numbers. 3, 55, and now 9. Making sense of that is very hard because he knows, well, the remainder is 9, the mod's 55, and it's some power of 3. Okay, so I have to think of a multiple of 55, which plus 9 makes a power of 3. First of all, how many multiples of 55 are there? Infinite. Add 9 to all of them, there's still infinite options. Finding out how many of those are multiple of 3, there's definitely more than 1. And then trying to calculate that is pretty difficult by itself with these numbers. And like I said, these get infinitesimally more complex. Just a ridiculous amount of complexity is involved with the actual calculation. And I'll show that in my next video. But for now, Bob still doesn't know where the message is. Note, the spy has no idea, but Bob doesn't even know. That's where the private key comes in. So this is a very important fact that we now have to utilize. I'm going to show how that is used. That is used by unlocking this box, essentially. So, just as the lock analogy served its purpose in the public key protecting the message, we're going to unlock the box. Now, in order to do that, I've split the sides into Alice's and Bob's side. So now that M is on Bob's side, we have no idea what M is, and we need to come up with a formula for it such that it uses the private key to somehow unlock the box, decrypt the code, and find out what M is only with the provided information. So, we do that first with the newest information that we just got, C. So M is equal to C to the power of the private key. No surprise that we're doing powers again, right? The power of the private key, keeping the same mod 55. Okay, this is a remarkable fact because it turns out that the private key, when you raise the code or the cipher to the power of that private key, even though it was involved nowhere in finding the cipher, when you raise the encoded message to the power of the private key, you actually end up with the original message. And because the private key is kept with Bob, there's no way the spy can find the message. So let's plug in our value for C. We now know C is 9, right? So we have an interestingly large number, 9 to the 7th. Now, just as the other example was a good way of showing how to do mods, this is a good introduction, and yes, simply an introduction, to show how complex this modular math can get and how hard it is for computers to do it. So, 9 to the power of 7, which you should take out your calculator to do, I hope, and if your calculator can't handle it, you should try Google, which can almost handle any power. 9 to the power of 7 is 4,782,969. Obviously, right? So 9 to the power of 7 is this big number, which I'll write right now. It is 4,782,969. Still mod 55, we haven't done that yet. And now we have a number to physically take mod 55 of, and that's our big number, 7 million, about almost 5 million. And that's small. This is one of the smallest examples I could have thought of, and it gets much bigger, I promise you. But let's do this for now. So 4,782,969. You divide that by 55, divide that by your mod, and you get a whole number and a fraction. That tells you that it doesn't fit in evenly, it doesn't fit in perfectly, and you would expect it not to. Thus, we take our number, which is 86,963.1 something. So 86963. Whatever that whole number is, we're not concerned with what that is. We take it away. We get rid of it right away because that represents what is in the remainder. So, take the answer, this decimal, subtracted by the whole number. For me, it's 86,963. You should get the same thing. And I got 0.072727. So, if you wanted to find the remainder, you could do 55 times this decimal, which is 0.072727. Multiply it by 55, and we get 4. So, it's no coincidence that the remainder of this huge number, when you divide it by something as small as 55, is, as the formula told us it would be, the message 4. And that is just a simple example of how, whoops, with the ugly 4. That is just a simple example of how the spy, who has all this information, which is given over cyberspace, has no way of finding this message due to the unique and clever private key, which in the end saves the day because of how large the power can be. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video in my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.